Hello everyone. Today I am going to explain about the different techniques for the testing. Okay, so here we have three basic or main approaches of testing techniques. That is nothing but ad hoc testing, scan-based techniques, and built-in self-test technique. Okay, so here we have three main approaches to what is commonly called design for testability. These may be categorized as follows. The first one is ad hoc testing, second one is scan-based approaches, and the third one is built-in self-test. Okay, so here first we will discuss about the ad hoc testing. Okay, so here if you observe this one, we have different ad hoc testings depending on the circuit condition and depending on the circuit what are the different elements we have. Okay, so that is what here ad hoc testing. So in this one, the first one is partition and mux techniques. So what is this partition and mux techniques? So if you have a large number of gates in this, that is a very large number of gates we have in the circuit under test or the device under test, then what we will do is we will partition that circuit into sub-circuits, and in between that we will place multiplexers and we will apply the test vectors so that there will be a more accessibility to the testing or test vectors to apply. Okay, so that is what the first one here, the partition and mux techniques. Since the sequence of many serial gates, functional blocks, or large circuits are difficult to test, such circuits can be partitioned and multiplexers can be inserted such that some of the primary inputs can be fed to the partition parts through the multiplexers with accessible control signals. So this is what the point partition and mux techniques. After partitioning the large circuits into sub-circuits, we are placing our multiplexers in between those sub-circuits so that we can apply the control signals and at the same time the test inputs or test vectors. Okay, so that is what here we have the partition. So the example I have considered is partition and mux method for large circuits. Here this is the totally actual large circuit, but it is divided into sub-circuit 1, sub-circuit 2. In between that, I am applying my multiplexer, and at the same time next sub-circuit 3, like that I am applying or I am placing in between these sub-circuits for easy way of testing or easy applying of these control signals. Okay, so that is what here control or test vectors we can apply here, right? So this is the example we have. With this design technique, the number of accessible nodes can be increased and the number of test patterns can be reduced. Okay, so with this design technique, what happened here? What is the advantage? The number of accessible nodes will be increased and the number of test patterns can be reduced. The number of test patterns can be reduced means automatically the power will be reduced and the delay time is also will reduced. Okay, so that is the first technique, ad hoc testable design techniques. Okay, the second one is initialize the sequential circuit. Okay, so initialize the sequential circuit means here we have the sequential circuit is a combination of combinational circuit with the memory elements. Okay, here the memory elements means that is nothing but the flip-flops. We don't know what is the initial state of that flip-flop or that sequential circuit. Okay, so what we will do is we will initialize the state with the known value. After that, we will apply the test vectors so that it is very easy to observe the outputs for the given test vectors. Okay, so that is the point here. Initialize the sequential circuits. When the sequential circuit is powered up, its initial state can be a random one. Okay, we cannot predict that initial state of that sequential circuits. Okay, so when the sequential circuit is powered up, its initial state can be a random and unknown state. In this case, it is not possible to start the test sequence correctly. Okay, so if you don't know what is the state of that sequential circuit, it is not possible to apply the test vector test sequences. Okay, so to avoid that, what we will do is we will initialize this sequential circuit for the known state, right? So the state of sequential circuit can be brought to a known state through the initialization. So that's what here the second technique what we have in terms of sequential circuits. Initialize the sequential circuit, right? Through the initialization. Next, in many designs, the initialization can be easily done by connecting asynchronous preset or clear input signals from primary or controllable inputs to the flip-flops or latches. Okay, generally the sequential circuit means it is a combination of combinational circuit including with our memory elements. That memory elements generally is we will consider is the basic memory elements is flip-flops or latches. So if you consider any flip-flop, it has its own state. Okay, so that's why how you can initialize that sequential circuits before applying the test vectors is nothing but in many designs, the initialization can be easily done by connecting asynchronous preset or clear input signals from the primary or controllable inputs to the flip-flops or latches. Okay, so asynchronous preset or clear input signals from primary or controllable inputs will apply to the flip-flops. Okay, that is what here the initialize the sequential circuit. Next one is disable internal oscillators and clocks. Okay, so when you are going to test a circuit, we have to disable the internal oscillators and clocks, because if you consider the internal circuits, internal oscillators or clocks, they will, what is the oscillator here means, they will generate the frequency signal or clock signals. Okay, so if you enable that one, so whatever the input test vectors we are applying, so that cannot be applied properly. That's why we have to disable internal oscillators and at the same time clocks. Okay, to avoid the synchronization problems during testing, internal oscillators and clocks should be disabled. Okay, so why means here, if you apply at the starting point some clock signal, but internally generated clock signal, they cannot match or they cannot synchronize, then if you apply the test vectors, we cannot verify the design correctly. That's why to avoid the synchronization problems during the testing, internal oscillators and clocks should be disabled. Okay, the next one is avoid asynchronous logic and redundant logic. Okay, here if you consider the synchronous circuit and asynchronous circuit, here the speed of this asynchronous circuit is very high as compared with the synchronous circuit. Okay, so the speed of an asynchronous logic circuit can be faster than that of the synchronous logic circuit counterpart. So the design and test of an asynchronous logic circuit is more difficult as compared with the synchronous logic circuit, and its states transition times are difficult to predict. As we seen that for a sequential circuit, how the initial state is not predictable. Okay, so similarly here we have here the asynchronous logic circuits. If the asynchronous logic circuit is there, if you want to test means, that is we cannot predict the transition times of these asynchronous circuit due to their speed of operation. Okay, so that is what here the design and test of an asynchronous logic circuit are more difficult than for a synchronous logic circuit, and its state transition times are difficult to predict. Why it is difficult to predict means the only one reason is the asynchronous circuits are very speedy. Okay, that's why here we cannot predict the transition times of these asynchronous logics. Okay, so then what we have to do? The operation of an asynchronous logic circuit is sensitive to the input test patterns, often causing the race problems and hazards of having momentary signal values opposite to the expected values. So what is these hazards and race problems means? If you consider a stuck at 0 or stuck at 1, that is nothing but what always it is applied with the stuck at 1. Suppose the output will be, we will get the different value as we cannot get expected value. Okay, so similarly here the hazards will be there. Okay, so what are the hazards means here? So if you apply some input, okay, so it cannot reach the input terminal in time. Okay, so in place of that, the previous value will be applied. Due to that, the required output we cannot get. So this type of faults or this type of problems we call as what? Race problems, and at the same time hazards. Okay, so the operation of an asynchronous logic circuit is sensitive to the input test patterns, often causing a race problems and hazards of having momentary signal values opposite to the expected value. Then what happened here? If there is a signal delay is there, that is input delay cannot reach the input point, okay, input terminal in time, then the previous input value will be applied, so that the output we are getting is for the previous value, previous input value, not for the present value. So that is a problem for us. That problem is called as here hazards. Okay, so this is about the hazards. Hazards is nothing but due to the delay in the input values to reach the input terminal. If you get the output is not same as that of the expected value, that type of problems we call as hazards. Okay, sometimes designed in logic redundancy is used to mask a static hazard condition for reliability. Okay, designed in logic redundancy is nothing but repetition of the circuit, repetition of the gates is called as redundancy. Sometime to get static hazard condition for reliability, we are going to use this logic redundancy. Okay, the redundant node cannot be observed since the primary output value cannot be made depend on the value of the redundant node. Okay, so these redundant nodes are used to eliminate the static hazards, okay, for reliability, but these cannot affect the output. Okay, so this cannot affect the output. That means what? The redundant node cannot be observed since the primary output value cannot be made dependent on the value of the redundant node. Okay, so it is unessential to test redundant nodes when they are designed in as backup parts, either to enhance the circuit reliability or to increase the fabrication yield. Okay, so only for this reliability only we are using, or we are using this redundant logics. Okay, but the testing cannot be applied to the redundant logic or redundant circuits because it cannot affect the output. That's why it is better to avoid asynchronous logic and redundant logic at the time of testing. Okay, so that is what here the use of redundant circuits can make test generation much more complex and difficult. Okay, so that's why we have to avoid asynchronous logic and redundant logics that are present in the testing circuit. Okay, so here this is the example what we can consider here, a redundant logic gate example. Okay, equivalent gate with redundancy removed. So if you observe this one, I will apply some inputs here. So here I will apply some values to this circuit, and whether it is equivalent to this circuit output I will see here. So if I apply here 0 and here 1, okay, that is A is equal to 0, A, B and C I am applying, A equal to 0, 1, 1. Okay, so if I apply that 0, 1, here we'll get it is 0 means here I will get 1. Okay, so 0, 1 for NAND gate, it is, I will get is here 1. And similarly here, if you apply this A to 0 here, I will get is here 1. Okay, and at the same time C value I will consider as 1 here, so that it is a NAND gate, so the output you will get is 0. Okay, so next what we have here is 1, right? So here also we are getting 1. Okay, so next here we'll get B is equal to 1, right? So it is an AND gate and I will get here 0. Okay, so if I apply this one, what I will get here, it is NAND gate, I will consider here 1, output is 1. So the same values if I apply here, okay, so because here the redundant circuit is removed here, redundant gate is removed, that gate is this one. Even though if I remove this, what I will get, I will see here. So if I apply A is equal to 1, A is equal to 0 here, 0, and B is equal to 1. So B is equal to 1 means here I will get 1, and C is equal to 1. Okay. So here it is 0 and 1. So we'll get NAND gate means it is 1. Okay. NAND gate truth table is 0, 0. I will get 1, and 0, 1. I will get 1, and 1, 0. I will get 1, 1, 1. I will get 0. Okay. So this is about the NAND gate truth table here, and F is the output. Okay. So now similarly here, if I apply A is equal to 0 here and B is equal to 1, so this gives the NAND gate 0, 1 means I'll have the output is 1 here for this NAND gate. Similarly here, the A is what? Inverted, that is 1 will get, and C is actually it is 1. So I will get 1, 1. So 1, 1 means here it is 0. Okay, 0 and 1 means F is equal to 1. Okay, so if you observe these two circuits, here what is this one here? Even though if you remove this one, this circuit or this gate, I am getting the same output. Okay, if you observe this, NAND gate and NAND gate is there, and A and B are connected to this, and the inverted in output is connected to this NAND gate. So the same circuit will be repeated here, except this redundancy circuit. Okay, but even though if you remove this redundancy circuit, or if you avoid this redundancy gate, so you are getting the same output. Okay, so here it is a redundant logic what we are used for the reliability, but here if you don't use this one also, we'll get the same output. So here, due to that, while testing a circuit, we have to avoid the redundant logic. Okay, that's what here we have. Okay, so if you consider this, even though if you consider this NAND gate and this without NAND gate, both are giving the same outputs for the given values of the test vectors or inputs. So that's why here it is mandatory to avoid this redundancy logic while applying the test vectors or testing. Okay, so this is what we have, redundant logic. That is nothing but one of the ad hoc testing that we can avoid the redundant logic. So that's what here, avoid asynchronous logic and redundant logic. So this is what we have. The bottom NAND gate is redundant and stuck at fault on its output line, cannot be detected. Okay, so this cannot be detected. So if you draw the remaining circuits, this will also give the same output. So there is no need of this one. Okay, so the bottom NAND gate is redundant and stuck at fault on its output line, cannot be detected. If a fault is undetectable, the associated line or gate can be removed without changing the logic function. Okay, so that's why this gate is removed, so that it will give the same output for us. Okay, so that is about avoiding of asynchronous logic and redundant logic in ad hoc testable design techniques. That is one of the technique. Next one is what? Avoid delay dependent logics. Okay, most automatic avoid delay dependent logic. If any delay dependent logic is there, we have to avoid that, right? Most automatic test pattern generation ATPG programs do not include logic delays. Okay, so generally these test pattern generators cannot be includes the logic delays to minimize the complexity of the program. As a result, such delay dependent logic is viewed as the redundant combinational logic. Okay, so these are the what we have here, the ad hoc testable design techniques. Okay, so the first one is what? We have to partition the large circuits and we have to use the multiplexers to apply the test vectors. That is the first one. Next one is the initialize the sequential circuits. We cannot predict after power upping of these sequential circuits. So to avoid that, to find the initial state of that, to find the correct state of that sequential circuit, we have to initialize with the known values. Okay. So next one is disable internal oscillators and clocks. To avoid the synchronization problems, we have to disable this. Next one is avoid synchronous logic and redundant logic. Redundant logic is nothing but it cannot affects the, it cannot, that circuit or that gate cannot affects the output. Okay, so that at the time of testing, we can avoid that redundant logic. It cannot influence the output. Okay, so therefore, in the testing process also, we cannot test these redundant gates or we cannot apply the test vectors to these redundant gates. So that is what avoid asynchronous logic and redundant logic. And the final one is we have is avoid delay dependent logic. If you have any delay dependent logics, we can avoid them while testing the process. Okay, so these are the ad hoc testable design techniques we have. Okay, so next the second one is what? Scan based techniques. Okay, so here we have the scan based techniques. The controllability and observability can enhance by providing more accessible logic nodes with the use of additional primary input lines and multiplexers. Okay, however, the use of additional input output pins can be costly, not only for chip fabrication but also for packaging. So what we discussed here in the first case is in ad hoc testing, we are making that large circuits into partition, that is sub circuits, and we are applying we are placing the multiplexers and we are applying the primary inputs. But including of these additional input output pins is difficult while fabricating and packaging. Due to that, this disadvantage can be modified or can be rectified by using the scan-based techniques. Okay, so now we are going with the scan-based techniques, right? So the scan design technique is structured approach to design a sequential circuits for testability. Okay, for testing, the scan-based techniques is a structured approach to design the sequential circuits for testability. In this, scan registers with both shift and parallel load capabilities are used. Okay, in this scan-based technique, we can use the scan registers. Okay, scan registers are formed with the flip-flops. Okay, so in this, the scan registers with both shift and parallel load capability, that is serial and parallel load capabilities are used in this scan-based techniques. Okay, the storage cells in the registers are used as the observation points, control points, or both. Okay, so here we have the storage cells of registers is nothing but it is 8-bit register, means 8 flip-flops we have to use. That means each flip-flop can store 1 bit of information. So 8-bit register means we have to use 8 flip-flops. That is the storage elements what we have in these registers. And these registers storage elements can be used as a observable and controllable points or both. Okay, so that is the point here. The main important point here is nothing but in scan-based techniques, the scan registers are very important, and those are the in those ones we have the storage elements. Those storage elements will be used as the controllable and observable pinpoints. Okay, so that is what here we have. A sequential circuit consists of a combinational circuit and some storage elements. Using the scan design techniques, the testing of sequential circuit is reduced to the problem of testing a combinational circuit. So because of using this scan-based design techniques, the testing of this sequential circuit is very easy, and that falls to the testing of combinational circuit itself. Okay, so that is what the importance, that is what the advantage of this scan-based technique. Okay, so a sequential circuit consists of a combinational circuit and some storage elements. Using the scan design technique, the testing of sequential circuit is reduced to the problem of a testing combinational circuit. Okay, so now we'll go with how the block diagram will be there for the scan-based design, or the general structure of the scan-based design. The mainly it consists of what? Scan path. Scan path is nothing but it is nothing but a memory elements, that is D flip-flops generally we used. Okay, so here we have in the scan-based design, the storage elements are connected to form a long serial shift register. If you connect here, if you observe here, this one is one, this one is another, this one is another. All these are what the storage elements. Generally, a sequential circuit consists of a combinational logic, including with the storage elements here. Okay, here the main important point is we have scan in input and the scan out. And at the same time, serial shift registers. Those registers are called as scan path, are also called as scan registers. Okay, so here the main scan-based technique is we have two types. One is two types of modes, that is in test mode and at the same time in normal mode. Okay, here we have in the scan-based design, the storage elements are connected. Storage elements are connected to form a long serial shift register. Then those are called as what? Scan path. By using multiplexers and a mode, that is, mode means here this scan based technique consists of two modes, that is test mode and normal mode. Okay, in the normal mode, all the flip-flops or the scan registers will be acts like a normal operation, but in the test mode, okay, so the testing process will take place. That is what here we have by using multiplexers and a mode control signal. So if you observe here, this is the mode control signal and this is the scan path, and we have scan in. Scan in is nothing but applying of the test vectors depending on the mode of the scan register. So if the mode is nothing but the test, mode control signal is test. Okay, then scan in will be applied and the final output or final path output will consider as the scan out. Okay, so in this test mode, the scan in signal is clocked into the scan path. That means here we have scan in that is placed into the what? The scan path. After that, and the output of the last stage of the latch or the flip-flop we are using is considered as the scan out. Okay, so in the test mode, the scan in signal is clocked into the scan path and the output of the last stage is scanned out. In the normal mode, the scan in path is disabled. Okay, so already I told that we have here two test modes. One is at the two modes of the scan registers or scan-based techniques. Out of that, first one is test mode. In this test mode, the the scan in signal will be applied to the scan path. Okay, so this is the scan path. At this point, I am applying scan in, and the output of last stage we will consider as the corresponding scan out, that is output value. Okay, so in the normal mode, the scan in will be disabled, and at the same time, the inputs will be applied to the combination logic and we will get the corresponding outputs. Okay, so this is about how we can have this general structure of scan-based design. Okay. Next one here, how we can test the sequence. What I told that is summarized here. Set the mode. So I have to test this circuit means first what I have to do, I have to take mode of the control signal that is in the test mode. Okay, so that is the point. So set the mode to test. Let latches accept data from the scan input. So if you place this test mode, then what happened is the scan in will apply the input signals. Okay, that is test vectors. Verify the scan path by shifting in and out of the test data. Okay, so here it will be obtained. The output of this one is connected to the input to this one, this output is connected to this, and finally we'll get the scan out. Okay, scan in the desired state vector into the shift register. Okay, that means we are applying the test vectors into this one by using the scan in process. Okay, apply the test pattern to the primary input pins, right? So these are the primary input pins. We are applying the test vectors. Okay, set the mode to the normal and observe the primary outputs of the circuit after sufficient time for propagation. Okay, next what here, assert the circuit clock for one machine cycle to capture the outputs of the combination logic into registers. Okay, now return the test mode, scan out the contents of the register, and at the same time scan in the test patterns. So like that, whatever you are getting at this point, scan out, and at the same time the circuit outputs, what we will got primary outputs, we will compare and we will predict the what is the defect or what is the false that will be obtained, whether the circuit is giving correct output or not. Okay, so this is the testing sequence of this scan-based technique. Okay, Here we have the storage cells in the scan design can be implemented by using what? Edge triggered flip-flop. Okay, master slave flip-flops are level sensitive latches controlled by the complementary clock signal. Already I told that here edge triggered flip-flops can be used, or master slave flip-flops can be used, or level sensitive latches can be used as the storage cells. Okay, the sequential circuit consists of storage cells. The storage cells is these types. Okay, an important approach among scan-based design is the level-sensitive scan design. It is nothing but what? Level-sensitive scan design, which incorporates both level-sensitive and the scan path approach using the shift register. An important approach among the scan-based design is what? Level-sensitive scan design. So it will incorporate both the level sensitivity and at the same time scan path approach using the shift registers. Okay, so what we discussed, the level sensitivity is to ensure that sequential circuit response is independent of the transient characteristics of the circuit, such as the component and wire delays. Okay, so what is the importance of including or incorporating this level sensitivity means? Okay, so it will ensure that the sequential circuit response is independent of the transient characteristics okay, of the circuit, such as the component and wire delays. Okay, thus LSSD removes the hazards and races. So what I told, hazards is nothing but due to the delay in the signal what we are applying. So we cannot get the expected outputs, that is called as hazards. So that hazards will be eliminated by using the level sensitivity. Okay. Next one is the boundary scan test method is also used for testing printed circuit boards and multi-chip modules carrying multiple chips. Okay, boundary scan test method is used to test these things, that is PCBs and multi-chip modules. Okay, on the negative side, that means the disadvantages of this one. For previous one, ad hoc testing, we have different disadvantages because the testing is difficult there. So we are going with scan-based techniques. It has its own advantage, but it has disadvantages also. Okay, on the negative side, scan design uses more complex latches, flip-flops, and input-output pins and interconnection wires, and thus requires more chip area. So to accommodate all these things, more flip-flops we are using, and at the same time input-output pins and interconnection wires. Because of that, the area occupied by this design technique, scan-based design technique, will be more. Okay, that means we have to provide more chip area for the testing. Okay, so that is one disadvantage we have. Okay, and at the same time, the testing time for test pattern is also increased due to the shift time in long registers. Okay, we are considering that here serial shift registers. Due to that, the test time will increases. If you use the parallel parallel registers, so the test time we can reduce. Okay, so this is about the scan-based techniques and at the same time ad hoc-based techniques. In the next class, I'm going to explain about built-in self-test technique. Okay. Thank you. Thank you for watching. Subscribe our channel.